Here. Yeah.
Need a copy?
No,
yeah, you can make sure people, if there's, we have extras here.
Sorry. That's really good. Spread out.
I didn't notice we were next to each other until you turned.
I got you.
Really? Yeah, no, it's exactly. Oh, this is awesome. My PyMOL is not working.
Well, you won't need it for a bit, and I'll give you a hand.
Yeah, it's not that it's not. I mean, it's not that it's my computer that's having a problem with it. I open it up and it goes like it flashes like for like an eighth of a second. It goes PyMOL.exe is not working. It makes me very sad.
Oh, why is this administrator?
Nope. Sorry. Yeah, that just makes me very sad.
Do we have Mac discussion?
No, I didn't. I mean, I just downloaded it.
Yep. Right?
Yeah.
Okay,
I
just
guess
want
I'm
to
gonna
make sure.
try.
Yeah, we do. I don't know
Don't
which
show
room
up
it
at one.
is.
Show up at one.
No, I'm just making sure.
Is it the same room?
Maybe, but
I
All right,
I
so
doesn't like it.
let me begin. So one of the reasons that I wanted to incorporate molecular modeling into spectroscopy is so much of what we do in spec is answering questions and analyzing specific situations. In other words, sure, some of it is you have a completely unknown compound, but a lot of times you're asking questions about stereochemistry or molecular conformation that are directly relevant to your research project. And being able to tie computer-based molecular modeling into spectroscopy is really, really powerful and very valuable. The other reason I do this here is it's a tool that I think every organic chemist should have in his or her toolbox. It ties so much into both synthetic organic chemistry and biomolecular structure that it's something that one really should have. We can basically, in about 1 hour, with maybe a little bit of an exercise afterward, become reasonably proficient in molecular modeling, or more specifically, what's called molecular mechanics. And as I mentioned last time, because my license for PyMOL basically allows me to distribute it to my students, I thought this would be a nice opportunity to share this with you. So what I want to do today is spend a few minutes giving a little lecture on what molecular mechanics is and the scope and limitations of molecular mechanics. Then I wanted to do a demonstration and show you a quick generation of a molecular model where you just watch. And then we'll do a little workshop where you'll go through and actually do this yourselves, and then we'll have a homework assignment, and that should be enough to read this. So the basic idea behind molecular mechanics is that one generates a conformationally realistic molecular model of a molecule and basically uses what's called a force field to do so. What a force field is a collection of parameters. And you're already familiar with the concept because this starts in sophomore organic chemistry. It is, for example, parameters for bond lengths. From the time you're a sophomore and certainly into the graduate level, you learn a carbon-carbon single bond wants to be about 1.5 angstroms, about 1.54 angstroms in length for an sp3 hybridized carbon. And so the force field knows that's the optimal length, and it'll treat your bond as sort of a harmonic potential, as a spring. And if you have to distort it and stretch it a little bit, you'll pay an energetic price, like a Hooke's Law spring. We know about bond angles in the same way. A carbon-carbon, sp3 hybridized carbon wants to have 109.5 degree angles. And if you distort it a little bit, say like we did in cyclopentane or cyclobutane in today's class where we were talking about strained rings, you pay an energetic price. And that also becomes a harmonic potential. And so you know as well things about dihedral preferences. sp3 atoms bonded together want to have a staggered conformation. Right from the beginning of sophomore organic chemistry, you learned that ethane wants to be staggered, and if it's eclipsed, you go up a sinusoidal curve and pay an energy price of about 3 kilocalories per mole for being eclipsed. And if you're a little bit off of an optimal 60-degree angle, you pay a little bit of an energetic price. There are also electrostatics incorporated. And we discussed this today in talking about bond dipoles. A carbonyl is polarized. There's a delta minus on the oxygen, a delta positive on the carbon. If you have another carbonyl and it has a delta minus and a delta plus, depending on their geometry, they can attract or repel each other. Other forces involve van der Waals interactions. Atoms like to touch, but if they touch too hard, they pay an energetic price. If they touch just a little bit, it's favorable. That's a van der Waals term. And then there are other things, for example, like salvation. And so what molecular mechanics is doing is basically using a computer to move over a multi-dimensional energy surface to get to an optimum geometry that minimizes bond distortions in length and angle and dihedral distortions and so forth. What molecular mechanics is excellent at is it's good for common structures and functional groups. In other words, parameters for bond lengths and angles and so forth have been well worked out for things like amides and ethers and aromatic rings and alkenes and amines and so forth, all the sorts of typical functional groups. What it's not good for is unusual arrangements of atoms, reactive intermediates, and so forth. Often metals and so forth, let's say transition metals. And so if one wants to generate a realistic picture of species like these, like a biradical, or perhaps a very unusual functional group that's not something you'd find in a typical textbook, you would end up wanting to use other computational methods, specifically electronic structure methods. such as those found in Spartan or Gaussian or TurboMol. All right, let me talk a little bit more about the concept of energy surfaces and so forth, and specifically one concept that we have to be very, very solid on. What molecular mechanics is doing is moving us down an energy surface to get to what's called a local minimum. And by local minimum, I mean moving down the energy surface until the, if you want to get technical, partial derivatives of energy with respect to each coordinate of motion are zero. In short, going to the bottom of an energy well. You understand this concept beautifully in 2 dimensions. And so let's take this, because you've had this built into what you've learned from so long. So let's take a look. I've drawn a Newman projection of Gauche butane. And in this particular conformation, our dihedral angle for Gauche butane is 60 degrees. And by contrast, you know anti-butane. I'll draw a Newman projection for it. Anti-butane, our dihedral angle, theta is 180 degrees. So I can write, and you've seen since sophomore organic chemistry, diagrams that look something like this. We plot our energy in kilocalories per mole versus our dihedral angle theta for butane. Go 0. I'm not much of an artist, as you may have noticed, so I'm going to put in a few tick marks to help myself. So I'm going to give myself a guideline here. 0.9. Another guideline here. 3.6, and another guideline here, and 4.5. And so if we look at the energy potential for butane as a function of theta, when we're fully eclipsed, when we're at a dihedral angle, we have an energy of 4.5 kilocalories per mole. As we rotate to Gauche butane, we have an energy, relative energy of 0.9 kilocalories per mole. When we go to 120 degrees, we have an energy, again, we eclipse as we bring this methyl eclipse with the hydrogen. We're at 3.5 kilocalories per mole. We rotate to 180, we hit the minimum of 0 kilocalories per mole. And then the whole thing repeats as we go around. And the energy surface looks something like this. It's basically like a cosine wave. Each of these points, Gauche butane, Gauche plus butane, Gauche minus butane, and anti-butane, are all minima. They're all specifically local minima. They are lowest energy points in their locality. If we start near Gauche butane, we move down the energy surface down to Gauche butane. If we start near anti-butane, we move down the energy surface to anti-butane. This is essentially what molecular mechanics is doing with respect to all coordinates of bond lengths and angles and dihedral angles and so forth. You're moving down until you find a local minimum. And for a big and complex molecule, it's not trivial, although there are plenty of algorithms to do it, to get from here to here. To put it another way, this methyl group doesn't know that it's even better to be over here than it is to be over here until it gets over the hill. It can't see that there's a deeper valley. We know because we've already studied the whole energy surface. But for big and complex molecules, it's tricky. So what molecular mechanics does is takes you to a local minimum, which means you need to engage your brain and think about global minima, or think about, or check out different local minima, or use an algorithm to do so. So all we're going to be doing today is learning how to generate some local minima for molecules in which there really aren't a whole lot of conformational options. Let me put this into concrete terms, getting away from butane to things that maybe are a little more familiar to you, or at least a little more relevant to you. If I start with cyclohexane with an axial methyl group, that is a local minimum. There's another conformation in which the ring flips to put the methyl group equatorial, and we know that this is the global minimum. I'm going to put that in parenthesis. It's also a local minimum. As is the other axial conformer. But without doing something specifically to flip from one conformation to the other, molecular mechanics is not going to automatically start here and get over here. Similarly, again, keeping to something reasonably familiar, if we start with boat cyclohexane, boat cyclohexane is actually a high energy point, just like over here. If we start with boat cyclohexane, we'll work our way down to the next local minimum. The next local minimum is the twist boat, twist conformation. And so we'll go from here to here. Actually, technically, in certain circumstances, if you're right on the very top of a symmetrical point, you won't actually go down because your partial derivatives here with respect to all energies are zero. But virtually every case you have substitution. If you start over here, you'll end up dropping to the next local minimum. All right. With this basic knowledge, you will keep out of a lot of trouble with molecular mechanics because you won't make unrealistic expectations. And so with that said, any questions at this point? All right, with that said, I want to run through a little exercise here, a little demonstration. Now, PyMOL is primarily developed as a visualization program, and the fellow who developed this basically kept adding to it and making it more and more sophisticated. At one point, the program grew a lot in size, and I sent him an email. I said, hey, what did you add to this? And he's like, oh, I built in a whole force field. It incorporates what's called the Merck molecular force field, which is actually a very good one for modeling a whole bunch of structures. There are a number of different windows here. We have a controlling window here. If you get geeky, there's a command line up here. We have a builder module here and visualization modules. there's a region here where you get different ways of displaying molecules. You can show things, you can hide things, you can label things, you can color things, you can do various actions. So A, S, H, L, C. This little matrix is sort of your guidepost here. The mouse does a lot of things in PyMOL. It can rotate, it can zoom, it can rotate about bonds, it can rotate parts of the molecule. And by a combination of keys and mouse clicks, you can do various things. For example, if you go ahead and you use the, well, I'll show you in the builder rather than here. So let me click on. There are two modes. There's viewing and editing. And if you, in the editing mode, for example, go ahead and use Control and the right mouse button, you can rotate about a bond. So if I have Gauche butane and I said, oh no, I want to start with anti-butane, you can rotate about the bond. Your left mouse does a lot of the selecting. Part of the thing that's frustrating is a lot of the knowledge doesn't really reside in your head for this. It's literally just in your hands, and so it's getting used to doing things on this. The other thing that's frustrating is the one thing that the program desperately, desperately, desperately needs is an undo. And it doesn't have it. So the one thing you want to get in the habit of is just every time you do something sizable and you don't want to lose your work, give a file name and save the file. So I'm going to do this. Don't follow along with me. Just watch me this time. You'll have a chance to do stuff on your own. I'm going to go ahead and build morphine. So I'm in the editing mode and I'm going to the builder. And when I go to the builder, it gives me a whole bunch of templates. And most of the building can be done with a template. If I want to build an alkyl chain, I can build it up from methanes. If I want to start with a benzene ring, I can start with a benzene ring. If I want an ene ring or a naphthalene ring, I can have that. In the case of morphine, I'm going to start with a cyclohexane, which is a nice starting point. So I just click, and you notice now it says some things here. It says create as a new object. And that means if I now click, I can go ahead and create as a new object. If not, I can attach to an existing atom, but I don't have anything yet as an existing atom. So I've created a cyclohexane. My right mouse button is the zoom, and so I'm zooming here. My left mouse button is rotate, and it's a little weird. If I get out here, my left mouse button is a Z rotate. So I'm going to be building for morphine, which is on your handout. I'm going to start by building the ring, the heterocycle that has the amine in it. So I'll just go ahead and start with the cyclohexane. I'll put in an equatorial methyl. I've now gone to the builder, click to attach the methyl. I'm going to click 2 times. Now I'm going to replace this atom with nitrogen here. And so that's the basic structure of the first ring of morphine. At this point, because this thing has a very pernicious tendency to go ahead and lose itself, I'm just going to give this thing a name, and I'll call it Morph A. All right, at this point, I want to put in the phenyl group of morphine. Again, morphine's on your handout. So I'm going to put in the phenyl group. I'll get the phenyl tool, and again, I've got to remember to click on it twice, pick location to, actually, I guess I don't, click location to attach phenyl. Here's the phenyl. The middle mouse button or scroll wheel allows me to bring the molecule down. If you're having trouble seeing in this form, because we're getting no depth, there are a couple of things I like to do. One of them is you can show as sticks, show as sticks, And another thing you can do is turn the display quality to maximum quality. And so I'm just going to zoom in. So that gives us a little bit of depth. I don't really need to, and I now want to add a carbon atom here and connect over to here to make the second part of the morphine framework. I can just add a carbon here and then form a bond over to this carbon. But in order to, at this point in the exercise, just show you a little more, I'm going to show you the rotate torsion function. So at this point, you notice in order to pick a torsion bond, I'm going to use the control and the right mouse button. So the control and the right, and of course, I didn't save. As I said, the program can be a little bit annoying. Depending on what you want to do, you can either just delete, nibble away. All right, now it says pick atom to delete. I'm going to say done. That's gone away in the upper left-hand corner. Pick torsion bond is control and right mouse button. Whoops, I'm back to the viewing mode. Whoops, what did I do wrong here? Of course. Oh, it's simply pick torsion bond is simply use control and right mouse button. So I use the control and the right mouse button. And now you notice it says control and left mouse button is rotate fragment. If I click on the top, it's going to rotate about the phenyl. If I clicked on the bottom, it would rotate about the cyclohexane. For me, it's easier to rotate about the bottom. As I said, this is largely superfluous here, but I wanted to demonstrate that function to you. At this point, I'm going to go back to delete, and it is, whoops, now I've got myself all flustered. Atoms, delete, delete. Okay. Now I'm going to go back and pick location to attach methyl. As I said, it's a little bit of an annoying program. And the last thing I'm going to do is create a bond between these two guys. Bonds create. Left mouse button is the standard thing. All right, now at this point, I have a molecule that's a little bit distorted. I'm going to go ahead and minimize. Remember, that means move down that energy surface. We're going to optimize our lengths and angles, primarily in this part. And they call it clean here. Clean is just their way of implementing molecular mechanics minimization. So I'll click on that, and you can watch what happens. And you notice it pulls together the slightly distorted bond lengths and angles become optimal. And at this point, I think I've said we'll call this morph B, save session. Whoops. If I save session, it's overwritten morph A, but that's okay at this point, save as. All right, the next thing I want to do is to build out the next ring of morphine, which is going to be a cyclohexane ring. So I will add a vinyl group. That's a carbon double bond carbon over here. And at this point, I'm going to just add some methyl groups. And we now have 6 that are going to make up our cyclohexane ring. So again, I'm going to create a bond. And clean it up. All right, and there's our cyclohexane. So I will now save session as. We'll call that morph C. All right, to finish up our morphine structure now, it's pretty easy. I have an alcohol, I have an ether, so I'm going to go ahead and I'll change. So this becomes an alcohol, This becomes an ether forming a bond down to here, so I'll do bond, create, click, click, and one more alcohol, and I have one. All right, so again we have a distorted structure, and now I just do my final minimization, and we'll call this, I will save it as morphine. Because I've already done this on my computer, I can override it. I want to demonstrate a couple of display options here. So I've already shown you that we can go ahead and show sticks or hide sticks. So maybe for this model, maybe I don't want to show my double bonds. I just want to show the conformation of the molecule. Maybe I'm interested in some NOEs. So I'm going to go ahead and do that. I've already gone ahead and remember I said make my display quality, maximum quality, so it already is. Let me get it into a nice conformation where you can see the cyclohexane ring, see the purity ring in a good conformation. Let me make it a little bit bigger with my right mouse button and go ahead and maybe I'll make the background white. Let's say I want to put this into a paper or into a dissertation. And then the last thing maybe to make it a little prettier, there's a ray tracing algorithm here. And you notice it does a little bit of rendering and so forth. And so at this point, maybe I'll go ahead and save the image as a PNG file that I can put into another document. Last thing I'll show you, just in case you like it, is under the actions, there are some presets. There's also a nice little ball and stick model if you prefer that. And again, I'll ray trace that. And make it nice and pretty. And save the image as just ball and stick. All right, well that's a little demo that's going to make you proficient. What I'd like to do at this point is to repeat this slowly and for you to come along with me on this and for Ryan to provide some support. So why don't you go ahead, I'm going to go and reopen my window here. And all right, so why don't you at this point join me and bring your laptops up. Ryan, why don't you check out and see if people are okay. So I'm going to pop in. Is everyone okay? And the Mac people okay? The X11 hybrid is all running for everyone? All right. So get familiar with your 3-button mouse, and we can go into the builder mode.
Oh, here we go. Yeah, let's start.
And you can go and choose a cyclohexane and create it as a new object. And maybe make it a little bit bigger. If you get in trouble, yeah, you can just you can just go ahead and clear. A couple of ways you can do it. One way is you can do, I think you can do it with the cycle.
Oh, is this?
I think you can go ahead and, you notice it's still on delete. Yeah, you had to double click.
Oh no!
This is one reason why saving is very, very useful here. And if you're having trouble at this point, and your neighbor isn't having trouble, neighbors, I urge you to help your neighbors.
No, it's just like I need to go through software first. Because like it's like I'm trying to open it up. So there's like a command prompt that pops up here, and then it just goes like I can't do it.
I'd say reinstall.
Yeah, that's what I'm trying to do. It worked okay before. It is, but
so just create a
yeah, right. Yeah, I'm just trying to do simplify things. Like, isn't that it's a 6-member ring? Right? I just need to get that double bond right there.
Wait, I have this.
click on there.
Alright, so check it out. So here,
I would say just
Can I do this?
It's not that smart, that's the problem. I'd say probably just
oh, where are your
What if I
hydrogens?
created like an individual?
Oh, don't hide the hydrogens.
just delete those two.
Oh, okay.
Yeah, it's a lot easier. Delete the CH3.
This guy?
Yeah. Add a pair, but either way.
Ooh, yeah. And then make a bond right here.
Yeah.
Yeah, you got it.
Every time I've done this, I always do 7.
There you go.
Let's go.
And then we have to go all the way to here?
Yeah, you make it more. So just.
How did you get it into like the thicker?
Oh, the
And maybe bring your quality on.
That is everything except multiple molecules, but it doesn't do show sticks. Create. So or you just select sticks. It's a lot easier to work with.
So I'm gonna at this point again add a methyl group because it looks like most people are coming along with it.
So how did you
So I'll add an equatorial methyl group, and I'll also convert over to a nitrogen atom here.
Yeah.
So go show the lines. It won't do anything because your lines are.
So that gives us our basic methyl and methyl pyridine structure.
Whatever, I'm just gonna do it.
This I'm just
I
gonna
have a okay, so I
Now you're at it. See?
Yeah, I just
Usually it's exactly what you
Do remember to save. Get in the habit here. I think this time I'm going to call this thing just as save session as we'll call it MOR. All right, at this point, remember I'm adding the phenyl group, and so I've gone and collected the phenyl tool, and I'm clicking on adding a phenyl. I'm using my middle mouse button to drag it down, and in part and I'm done, so I'm clicking done, and in part just to remind us of the rotation tool, I'm going ahead and using Control and right mouse button and clicking on the upper part of the bond. Just to rotate it around. Finally, I'll add a methyl group.
Save it.
I'm going to minimize it because it'll push it out.
That is the most.
Did you do it, Chris?
Yeah.
So did I. No, I didn't say it. What do you think of that?
I broke my benzene, but
I don't need to do
there.
Save
Session S.
Save session.
Just make sure. Oh, okay. If you want to, if you're completely done with work, you can save it over.
I'm making my bonds here, and I will try a double bond.
3D printers? How you doing over there, Luke?
Dude, I did it one try. It was like 2 tries, but I didn't say it. So. And mine's not green either; it's beige. Yours is rainbow. What did you do wrong? Real morphine or what? Oh, that is pretty awesome. How'd you do that?
How do you do the double bond?
Let's see, I built the ring individually, and then like when I got to this part, I just added a double bond part in there. You get what I'm saying? Like when you get to this point, just add the double bond part in there. Oh no, we have to make strychnine? I don't want to do that. It's hard to look at without having the computer. No saves.
No saves, one go.
Start the clock.
How do I get 3 tries?
3 tries, alright. No saves. That's how we're gonna make this class a lot.
I don't know how to get rid of morphine.
You clear.
Delete all. I can work that.
Really? Delete everything? They need a comma in this prompt. Oh, I did it.
You got it?
We can do strychnine if we did the
If you did morphine, and you can do strychnine, and if you want me to check your structures, you can email them to me.
Is that what we do? Instructor?
Well, right, the homework assignment has you hand in printouts, but if you want some feedback on your morphine or strychnine, you can email it to me as an attachment, and I'll take a quick look and let you know.
I don't want to save.
I'll do that sometime.
What?
I'll do that sometime.
You're gonna, yeah, looks like without being installed, you're out of it.
There we go.
So I remade my morph B structure, and at this point, I'm gonna make add my double bond again.
Yeah, it should be the right one. Oh, you're using.
Oh, I got
And
this
I'm
too.
gonna add a couple of methyls.
Or actually, no, I think that's
Oh,
the center.
middle, yeah. Thank you. That's so helpful.
Yeah, otherwise you have
The
to.
structure.
You get to hold control, or you have to hit both.
And that's my morph C.
For it to work. It's a pain.
Is there any you can select each one or no?
Yeah. That I think is actually control.
All right. Now the bad news is once you go to ball and stick, I don't know an easy way to undo it. So save your. That's okay. Save your structure first, and then when you reopen it, you'll get it the old way. Under
I just wanted to see if I
actions.
could.
So the question is, how do you get ball and stick? Under actions, A for the whole structure, you go to preset.
If I wanted to make this,
Ball
then
and stick.
What?
Oh no, attach it that way? No. You better have to.
And if you just want to go ahead and
So,
do it
I'll just do
as
it might be short.
sticks
I know
like
there's a
this,
way.
you
Hold
can
on.
do sticks and you can do, I always like to do
Oh,
quality
very nice.
quality.
But that's you're gonna get into trouble as far as stereochemistry goes.
Really?
If you don't build it
If
piece
I
by
don't,
piece.
if I clean it, will it not adjust?
Because 3-dimensionally, you see it's flat right there. But if
Right.
you rotate it, they might be off space.
If they're not covalently linked, they'll adjust, but it's going to be only based on van der Waals. Interaction.
You should start by like each carbon.
You should link them. So where are you at here?
I was trying to do this, then maybe delete
Oh, the
two,
strychnine?
add a nitrogen, and then create
Oh, okay. You could do that. Yeah, so you can go ahead, just delete them and create bonds.
Yeah, but well, in this case, the way that you have it, you have to bring this one forward.
But it'll be okay if you attach them there, you'll be fine.
Right.
Now, mind you, you had it here, so you actually had it, but that's okay.
Oh, you're right, yeah.
Yeah, but that's okay. Use create and create a bond.
that would be right here, right? And then right there.
Well, it looks like you're going to have one too many atoms, but
1, 2, 4. Oh, you're right. Sorry.
but yeah, you can do create bond.
I could delete this one.
Yeah, just create a bond. That'll be fine. It's a little cumbersome, but that's nothing matter for somebody beginning.
I don't know if it.
Create.
No,
Click, and click create now. Oh, maybe it
I
does.
think it has a
I don't
pop
think
with
it does. I don't think you're right. I don't think it does intermolecular.
No. Yeah.
Okay.
You get issues that way. Okay, so although if you were building it and you cut it apart, it still sees it as one.
Oh, you have a double bond to hydrogen. You made that. Make that
So like
into a carbon.
if you do the ethane, right? Cut off the
Wait, you're not
cut the
Oh,
ring
yeah,
off.
sorry, one more time.
You can still reattach it and it still sees it as one. If you do two new objects,
Now,
it doesn't
create.
it doesn't deal with that.
But somehow I fixed it.
Clean it up.
Tried clicking along there.
Something's wrong. You have a bond of hydrogen to hydrogen. You need to bond that benzene. Don't worry about deleting the hydrogen. Just create a bond between hydrogen here. And clean it up, and everything from there. There you are.
You can actually just go through
All right,
this
now you just need your oxygen.
Oh, I was just trying to come up with it here, probably.
There's some easy steps.
Oh, well, we got the first thing.
Why don't you go to sticks so I can so show sticks and let's go to quality maximum.
Probably the same second step, too.
Display quality maximum.
Oh, I think what you're talking about is syndrome.
Yeah.
Oh, no, you've got your rings after trading. I have no idea what you think.
You can do, if I'm not mistaken, you can export out Angel in a certain file format and it'll take it up in PyMOL.
Really?
But it doesn't do stereochemistry very well with the
Oh, your stereochemistry.
It's not the best option.
You notice your hydrogen is on the wrong side.
Yeah, stereochemistry.
So the good news is what you can do, that hydrogen should be pointing down. I think it should be pointing down. So what you need to do is delete this. Is basically what's the best way? This way will be delete this oxygen, put an oxygen here, put hydrogen back here, and then redelete it. Yeah, you made a really bad diastereochemistry.
What if you mess up your stereochemistry?
Just helping you one by one.
Yeah.
So, the way I see it,
Those are going to be cis hydrogens.
so that's correct, right?
Go to, at this point, go to stick. Go to stick and go to quality maximum. Show sticks. And, yep, sticks. And go to display quality maximum so I can see it better. Maximum quality. No, maximum quality.
And then just ray trace it.
Yeah, quality.
Maximum quality. There you go. Now I can see it. Those two are cis. Yeah, you're perfect.
So you can move it.
Yeah.
So I'm trying to clean up my structure.
All right, that probably your structure may be beyond what? All right, let's go and make it stick so I can see it better. Other problems. Display. No, not stick. Display. Go back.
Oh, you save molecule.
Display. Show. Sticks. And I'm kind of a stickler, so I just like.
Are you trying this in for homework?
Yeah.
We trying this for homework?
there's no force field that can save. God knows what's going on.
I think you can also read. I think if you.
I would nibble away at that and rebuild. Yeah, instead of nibble, delete all the atoms here. I think what's happening. God knows. Just delete the atoms. So delete, and you'll go delete the atoms. Just nibble all those away.
I have a question.
You may need to.
Clicking. Okay, so on the mouse, small mouse,
Do a
go
space
backwards.
color. Yeah, it's just like deleting.
Okay,
After making a bond. That's just what's happening.
Yeah, that's what happened.
There you go. That's this part going on there.
I would just look at
So click on, let's see, click on.
Honestly, I would do that. They're there. It simply isn't showing. If you go to display show balances, it'll recognize them. It's recognizing them based on the distance.
If you do, yeah. Still keep it on.
PDB is a more universal. So So this is a good question that was asked. So the question is, what's PDB and what am I talking about with PSE? PSE is the proprietary file format for PyMOL that has all of the information about how to render the molecule in it. PDB is this universal file format for atomic coordinates that has lots of people's atomic coordinates, that's compatible with lots and lots of different software. So the reason I asked you to do PDB is later on we're going to be transferring some files to a more sophisticated program that will allow some coupling constants to be easily calculated, and I wanted you to get the feeling for outputting in that file format. Well, I'm going to finish up my molecule here, and if anybody wants to email me theirs to look at, I'll be happy. We probably, I guess we're coming to the end of our discussion section here, so I probably should be willing to let you go, but if anyone wants to email me, I'll give you a quick feedback. Here's my redo of morphine.
You can give it up to the side.
Especially
I would just delete that right there, the CH2.
Looks like nobody has emailed me yet, but if you want to send me one, I will give a quick critique. We're done. Yes, if you want to stick around, you can, but we are officially done. And what's that? So I think this is due with next week's homework set. So, and if you want